All right, so we're diving deep today into this research paper you gave me.
Yep.
An operating principle of the cerebral cortex and a cellular mechanism for attentional trial and error, pattern learning, and useful classification extraction.
Yeah,
It's a mouthful.
it is.
But the core idea here is really intriguing.
Yeah.
How do individual brain cells learn?
Right.
And how does that scale up to consciousness, free will, maybe even defining what intelligence is?
Yeah, so the paper starts by really focusing in on one very specific type of neuron called the pyramidal neuron.
Okay.
And most of your neocortex, the wrinkly outer layer of your brain, is made up of these things.
Neurons, neocortex, got it.
Yeah.
But what's so special about these pyramidal neurons? What makes them different from other neurons?
Well, they're not just simple on-off switches, right? They're more like these complex, multi-part processors.
Okay.
And what this paper is proposing is that these pyramidal neurons act as something they call reward-modulated combinatorial switches.
Reward modulated combinatorial switches.
Meaning they don't just react to like one signal.
Right.
They learn to recognize combinations of signals
Okay.
that predict that something good is about to happen.
So my brain is basically a prediction machine, constantly trying to figure out, based on past experience, what's coming next.
Yeah, that's the idea.
Okay.
And these pyramidal neurons are key to that whole process.
Okay.
And they have these two distinct parts to them.
Okay.
You have the apical tuft, which is at the top, and the basal dendrites at the bottom.
Right.
And one way to think about it is like a tree,
Okay.
where the apical tuft is like the branches reaching up, gathering information from all these other brain regions.
Okay.
Almost like running simulations.
Right.
Or making these guesses about what to do next.
Interesting.
And then you have the roots, which are the basal dendrites, and that's where the actual learning takes place.
Okay, so the basal dendrites, the roots, are where the actual learning is happening.
Right. The basal dendrites are receiving input signals from all over the place.
Okay.
And they form these clusters of synapses that respond to specific patterns.
Okay.
And if a pattern leads to a reward, something good happening,
Right.
those connections get stronger.
Interesting.
It's like the neuron is building up this library of successful classifications.
Makes sense. You get rewarded for something, you're more likely to do it again.
Right.
But what about when things go wrong? We don't just learn from the good stuff.
Right.
We got to learn from our mistakes too.
That's right. Yeah.
How does the paper address that?
Yeah, so the paper actually connects this model to something called behavioral timescale synaptic plasticity, or BTSP.
BTSP?
BTSP, yeah, it's a mouthful.
Right.
But it's basically a way that brain cells can adjust their connections over time based on experience.
Okay. Both positive and negative. So it's not just about reinforcing the good choices.
Right.
It's also about weakening the connections that lead to bad outcomes.
Exactly.
So we're less likely to make those same mistakes again.
Exactly. And what the paper suggests is that this
BTSP
is happening not just at the level of individual neurons, but at the level of these larger networks in the brain.
So we've got these pyramidal neurons learning from their mistakes, but how does that translate into something that we actually experience? Like, how do we become aware of this learning process? I mean, are we consciously aware of every little synaptic connection being strengthened or weakened?
Yeah, that's a great question, right? So what the paper proposes is that there's a very specific type of firing in these pyramidal neurons.
Okay.
That is the neural correlate of attention,
Okay.
and it's called BAC firing.
BAC firing?
Yeah.
Catchy name.
Yeah, so it's like a signal flare going off saying, hey, this is important, pay attention to this pattern.
Okay, seriously though, what triggers this BAC firing?
So remember the apical tuft?
The branches?
The branches, yeah, the part that's making those guesses.
Right.
When one of those guesses is correct and it leads to a reward,
Yeah.
the neuron fires in this very specific way.
All right.
And this burst of activity strengthens those connections even further.
So it's like a double whammy.
Yeah.
The neuron makes a good prediction, gets rewarded for it, and then this BAC firing basically cements that.
That's the idea.
Okay.
And what they're arguing is that this burst of activity, this BAC firing, might be what we experience as that ha moment.
Oh, wow.
That flash of insight when you suddenly understand something.
Okay, that's pretty cool.
Yeah.
So individual neurons are making predictions, learning from both successes and failures, and then signaling when they've hit on something important.
Right.
But this is all happening at the microscopic level.
Right.
How does this scale up to the complexity of the whole brain? I mean, we're not just a collection of neurons firing randomly, right?
No, not at all.
There's got to be some kind of organization.
So that's where things get even more intricate.
Okay.
These pyramidal neurons aren't just scattered throughout the cortex.
Okay.
They're organized into these tightly packed columns.
Okay.
Well, minicolumns.
Minicolumn.
Yeah, you can think of them like these little neighborhoods of neurons
Okay.
all working together.
So what's going on in these neural neighborhoods?
Well, the paper proposes that these minicolumns as these tiny little learning units.
Okay.
And there's this phenomenon called depolarization cross-induction.
Depolarization cross-induction.
Yeah.
All right.
That occurs between neurons within a minicolumn.
Okay.
And basically what it means is that one neuron firing can trigger its neighbors to fire. So you get this chain reaction of learning.
Like a domino effect of aha moments.
Yeah.
So we're going from individual neurons to these collaborative learning teams.
Exactly. And what the paper suggests is that this is how these more complex representations of the world get built.
Okay.
It's not just about individual features. It's about how those features relate to each other.
Okay.
How they form patterns and categories that help us make sense of our surroundings.
So these minicolumns are basically building up a model of the world based on their experiences.
Yeah.
But where does the information about what's good and bad, what's worth paying attention to, where does that come from in the first place?
Yeah.
I mean, there's got to be some kind of feedback system, right?
Yeah, you're absolutely right.
Some way of telling these neurons what to focus on.
There is.
What is it?
And that's where the medial temporal lobe, or MTL, comes in.
MTL. Okay.
And the paper really highlights how crucial this part of the brain is in this whole process.
Okay.
You can think of the MTL like your brain's novelty detector and reward evaluator.
Like a built-in critic constantly watching and judging our brains perform.
In a way, yeah.
Okay.
The MTL is constantly comparing incoming information to past experiences.
Okay.
And when it detects something new or surprising,
Okay.
it sends signals to the cortex.
All right.
And that can trigger those attention-grabbing bursts of activity that we were talking about earlier.
So the MTL is basically saying, hey, cortex, pay attention to this. This is new. This is potentially important.
Right.
And then the cortex, with its pyramidal neurons, its minicolumns, it gets to work figuring out what it all means.
That's a good way to put it.
Okay.
But there's another layer to this as well.
Okay.
What the paper suggests is that the MTL isn't just responding to external stimuli, like what's happening right now.
Okay.
It's also involved in recalling memories, but even anticipating future events.
Wait, hold on. So our brains are using past experiences to predict what might happen next.
Yeah.
And then using that information to guide attention and learning.
That's the idea.
It's like we're constantly trying to stay one step ahead of reality.
Right.
Wow.
And the paper's arguing that this predictive ability,
Right.
this interplay between the MTL and the cortex,
Yeah.
is a key part of what we consider intelligence.
So we've got individual neurons acting like tiny learning machines.
Right.
Organized into these collaborative minicolumns.
Yeah.
All guided by this novelty detecting, reward evaluating, future predicting MPL.
That's right.
That's a lot to take in.
It is.
I think we need to pause here for a moment, let this all sink in.
Yeah, definitely.
We've got a lot more to unpack here.
Yeah.
And we'll delve deeper into some of these really mind-bending implications of this model in just a bit.
Yeah, we'll be back.
Stay tuned.
So before the break, we were talking about how the medial temporal lobe, the MTL,
Right.
is helping to direct your attention.
Yeah.
It's constantly comparing what you're experiencing now to what you've experienced before.
Right.
And using that mechanism, we talked about BTSP,
Right, BTSP.
behavioral timescale, synaptic plasticity to
Yeah.
flag anything unusual.
Like the MTL is sniffing out novelty.
Right.
Anything that breaks the pattern of our expectations.
Exactly. And when it finds something novel,
Mhm.
it sends signals to the cortex, right?
Yeah.
Prompting those attention-grabbing bursts of activity in those specific pyramidal neurons, like saying, hey, cortex, analyze this. This might be important.
Okay, so the cortex is where the deep learning, the categorization, the memory formation.
Right.
That's where it really gakes in.
Yeah.
But it's the MTL that's acting like a filter, highlighting what's worth learning in the first place.
Precisely.
Okay.
Now, think about how you learn a new skill, right?
Okay.
At first, it takes conscious effort. You have to focus. But eventually, it becomes automatic.
Like riding a bike.
Yeah, exactly.
You don't have to think about it anymore.
You just do it.
Right.
What the paper suggests
Okay.
is that this transition
From equifull to automatic.
yeah, from attentional to automatic processing
Okay.
is reflected in how these pyramidal neurons fire.
Wait, hold on.
Yeah.
How can you tell what kind of processing is happening just by looking at how a neuron fires?
So the paper proposes this, well, it's fascinating. I think this whole classification system for these pyramidal neuron excitations,
Okay.
and it divides them into these four categories.
Four categories. Okay.
So you've got attentional versus automatic,
Okay.
and then you've got voluntary acquired versus involuntary.
All right, that sounds a little complicated. Break it down for me.
Okay, so first,
What's the difference between attentional and automatic?
so attentional excitations,
Okay,
those involve the apical dendrite,
right, the branches.
the branches of our tree.
Yeah, our tree analogy. Okay,
And they require conscious effort.
okay.
So think about like learning a new language or solving a complex problem, right?
Yeah.
You're actively engaged.
Yeah.
Your attention is focused.
Got it.
So automatic excitations are basically the opposite.
They happen without us having to consciously think about them.
Right. It's like, yeah, riding a bike or typing on a keyboard.
Right, once you've mastered it.
Yeah, after you've learned it.
You don't have to think about it anymore.
Exactly. The training wheels come off.
Okay.
Now, within each of those categories, attentional and automatic,
Uh-huh.
there's another distinction, and that's voluntary acquired versus involuntary.
Okay, you're losing me a bit.
Okay.
What's the difference there?
So voluntary excitations are those we consciously initiate.
Okay,
Like you choose to focus on a particular sound.
right.
You decide to move your arm.
Got it.
Involuntary excitations.
Okay.
That those are triggered by things but are outside of our control.
So sudden loud noise?
Yeah,
A painful sensation.
exactly. Things like that.
So even within the realm of things we're paying attention to,
Right.
there's a difference between what we choose to focus on
Yeah,
and what grabs our attention whether we like it or not.
precisely.
Interesting.
And here's where it gets even more interesting.
Okay.
The paper suggests that voluntary attentional actions, the ones we consciously choose to do,
Yeah.
they become automatic with learning.
That makes sense. The
Yeah.
more you practice something,
Yeah,
the less you have to think about it.
exactly.
But what about involuntary attentional actions?
Right.
Can those become automatic too?
That's where the paper draws this key distinction.
Okay.
Involuntary attentional actions.
Yeah.
Those are hardwired. They're like these
Okay.
essential survival mechanisms.
Makes sense.
Right. You wouldn't want to ignore pain
Yeah.
or a potential threat just because you're engrossed in a good book or something.
Right. Your brain's got to be able to override whatever you're consciously focusing on.
Exactly. So there are these certain things
Yeah.
that our brains are wired to pay attention to,
Okay.
no matter what else is going on.
It's like there's this separate system running in the background.
Right.
Always on the lookout for danger,
Exactly.
keeping us safe.
Now let's tie this back to the concept of voluntary control.
Yeah.
That big question of free will.
I bring on the deep thoughts.
Okay, so this is where the paper gets, pretty philosophical.
Yeah.
But how does a model based on, neurons firing explain something as complex as free will?
Right. Exactly.
So what they're proposing is that the apical tuft,
Right.
that top part of the pyramidal neuron,
Yeah, the branches.
the branches where all the guessing is happening,
Right.
might be the seat of our voluntary control.
Okay.
It receives feedback from all over the brain,
Uh-huh.
including areas that are involved in planning and decision-making.
So it's like the apical tuft is the executive office of the neuron,
Okay,
integrating information from all the different departments, and then deciding on a course of action.
that's a good analogy, yeah.
All right.
By combining information from all these sources. The apical cuff allows us to, choose our action.
Or at least it gives us the feeling of choosing.
Yeah, right.
Okay, but how does this model account for those times when we act impulsively?
Okay.
Or when we're not really sure why we did something,
So remember those involuntary attentional excitations we were talking about?
right?
Those can override our conscious intentions,
Okay.
especially when it comes to those basic survival instincts.
Right, fight or flight.
Exactly.
Yeah.
And sometimes even our voluntary actions might be influenced by factors that we're not fully aware of,
Like what?
like past experiences, subconscious biases,
Uh-huh.
even just our current emotional state.
So it's not just a simple on-off switch between
No.
conscious will and automatic
It's
responses.
more complicated than that.
It's more like this complex interplay of multiple systems
Yeah,
with varying levels of awareness and control.
precisely.
Okay.
And this model is suggesting that our sense of free will
Yeah.
might actually arise from this very complexity.
Interesting.
This constant awareness between conscious intentions, unconscious influences,
Mhm.
and those hardwired survival mechanisms.
This is giving you a whole new perspective on what it means to be in control.
Yeah,
Okay, but I want to go back to something you mentioned earlier.
okay.
Those internal representations of the external world.
Right.
How are those actually formed in this model?
So this is where things get really fascinating.
All right.
Remember those minicolumns?
The little neural neighborhoods?
Yeah, those little teams of neurons working together.
Yeah.
What the taper's suggesting
Okay.
is that they're not just learning these individual classifications, they're combining them
Okay.
to create this much richer, more complex
Right.
internal model of the world.
So each mini collie is like a piece of the puzzle.
Right.
And together, they form this complete picture of reality.
Exactly.
Okay.
Now, remember those two types of pyramidal neurons we were talking about?
The PT neurons and the IT neurons.
Yeah.
The doers and the thinkers.
That's a good way to put it.
Right.
So what the paper proposes is that the IT neurons,
The thinkers.
yeah, the thinkers,
Okay.
might actually piggyback off the activity of those PT neurons.
The doers.
Yeah, within a minicolumn.
Okay.
They use that depolarization, cross-induction.
Right, the domino effect.
Exactly, to essentially, well, learn from the PT neurons' actions.
So it's like the IT neurons were watching the PT neurons and taking notes.
Yeah.
Like, okay, that action led to that outcome. Interesting.
Exactly. They're building up this internal representation of the world.
Okay.
Based not just on what they sense directly,
Okay.
but also what they learn by observing the consequences of actions.
This is blowing my mind.
Yeah.
Our internal models of reality.
Right.
They're not just these passive reflections of sensory input.
No.
They're actively shaped by our actions.
Yes.
And the outcomes of those actions.
Exactly.
But how does this all connect to language?
Right.
I mean, we use words to represent these concepts, these ideas.
Yeah, it's a crucial question.
How does this model explain that?
So the paper tackles that head on.
Okay.
And what it proposes is that language itself might actually be a product of these same classification mechanisms we've been talking about.
Oh.
Okay. I mean, think about it. Words
Yeah.
are labels for categories,
Right.
for classification.
Right. The word apple is a label for a category of objects
Exactly.
that share certain features.
Yeah. Roundness, redness, certain taste,
Okay.
and so on.
Yeah.
And what the paper argues
Okay.
is that the way our brains group words into these categories
Right.
might reflect the underlying structure of our internal world.
Interesting.
The way our pyramidal neurons have classified information based on experience.
So the categories we use, the way we structure sentences, it's all mirroring how our brains are classifying information.
That's the idea.
It's like language is a window into the inner workings of our minds.
That's a powerful insight, yeah.
It really is.
And it opens up these whole new ways of thinking about it, how we
Yeah.
communicate and understand each other.
We've gone from single neurons
Right.
to these collaborative metacolumns.
Uh-huh.
Explored the role of the MTL.
Yeah.
We dive deep into free will and attention.
Yeah.
And now we're connecting it all to language.
It's a lot.
This paper is truly ambitious.
It is.
But I have one more question before we move on.
Okay.
How does this model explain problem solving?
Okay.
I mean, it can't just be about classifying information, right?
That's a great question. And so in this framework, problem solving can be seen as this process of testing out different classifications
Okay.
until you find the one that leads to the desired outcome.
So it's like trial and error at the neural level.
Kind of, yeah.
Our brains are constantly running these simulations,
Right.
testing out different classifications to see what works. And
Exactly.
when we face a challenge,
Yeah.
our brains essentially cycle through these different classifications,
You're right.
trying to find a match that will lead to a solution,
Yeah, and each success strengthens those connections.
right? Reinforces those pathways.
Exactly, refining our approach.
So it's like our brains are learning by doing,
Right.
even if that doing is happening entirely within our own minds.
Exactly.
So every time we solve a problem, we're not just finding the answer.
Right.
We're actually making our brain's classification system more sophisticated.
That's the idea.
Wow.
And this learning process doesn't even require conscious awareness.
Right. It can happen in the background all the time.
Constantly shaping our understanding of the world.
Right.
And our ability to solve its challenges.
But here's where things get even more interesting.
Okay.
And where this paper starts to push the boundaries of what we currently understand about intelligence.
Okay.
What is it?
The paper asks this really profound question.
All right, I'm on the edge of my seat.
Could these principles of classification and reward-based learning be fundamental to any intelligent being, not just humans?
Wow. Okay, now we're talking about the nature of intelligence itself.
Right.
This is getting pretty cosmic.
Yeah.
I think we need to take a moment to let this sink in
Definitely.
before we explore those implications.
Yeah.
We'll be back soon to wrap up this deep dive and discuss what this all means for you. Okay, welcome back. So before the break, we were about to get into some pretty big questions, right? Like this paper we're looking at, it doesn't just propose a model for how our brains learn. It suggests that these principles could be fundamental to any intelligence, no matter where it is.
Right, that's the big implication. The paper argues any intelligence evolving in a universe, let's say, with consistent laws of physics, would likely face some of the same challenges.
Meaning it's not about the specifics of the human brain. It's more about fundamental principles of like learning and solving problems that might just be universal.
Yeah, I mean, think about it. Our world has patterns, right?
Right.
The laws of physics are consistent. Things fall down, not up. Cause and effect, you know?
Right. Makes sense.
And this predictability allows for, well, classifiable information, right?
Right.
And recognizing these patterns, well, That's key for survival.
Yeah, if the universe were totally random, there'd be no point in learning because there'd be no way to predict anything.
Exactly. So any intelligence, no matter what it's made of, it would probably need to develop ways to classify information, to predict what's going to happen, and learn from what happened before. And this paper says the model we've been talking about, the reward stuff, the minicles, the MPL, it might be a blueprint for how any intelligence could even come about.
So we're not just talking about the human brain anymore. This research could change how we think about the very nature of intelligence anywhere in the universe.
Yeah, that's the core of it. And it makes you think about AI too, artificial intelligence right here on Earth.
Like, this research could help us build smarter AI.
Well, AI today is powerful, sure, but they don't have the flexibility, that adaptability, like biological intelligence?
Right. They're good at specific things, but they don't generalize well or really learn from new stuff the way people do.
Yeah. And this model might give us like a roadmap for AI that's more in line with how biological intelligence actually works, systems that learn faster, adapt, maybe even develop something kind of like consciousness.
That's getting pretty wild to think about. So this isn't just theoretical neuroscience. It could actually impact how we build AI down the road.
It's possible, yeah, a lot more research to do, but this paper lays out a way of understanding what might be like the universal principles of intelligence.
So after all this, what's the takeaway for our listeners? What does this all mean for how we think about our own minds and how we learn?
Well, your brain is doing more than you probably realize, right? It's not just passively taking in information, it's actively classifying things, predicting and learning at every level from the single neurons to whole regions of your brain.
It's like our brains are constantly running these algorithms, getting better at understanding the world without us even knowing it.
Yeah, and this model we've been talking about gives us a peek into how those algorithms actually work. It shows how important reward is and attention, how different parts of the brain work together.
So the next time you have that aha moment or you figure out a tough problem, you can picture all that neural activity that made it happen. Those pyramidal neurons, the minicolumns, the MTL, keeping you on track.
And maybe someday, we'll not only be able to build smarter machines because of this, but maybe even recognize and talk to other intelligences out there, no matter how different they might be from us.
That's something to think about. If intelligence isn't just limited to us, what else is out there?
Right. It's a question worth exploring.
We've known from the mechanics of how neurons work to what intelligence itself is, even touched on the possibility of other life out there. It's been quite a deep dive, as always. We hope you've enjoyed it and come away with a new appreciation for how amazing your own mind is. Until next time, keep those neurons firing.